Okay, I would like to start just thank you, saying thank you to the organizers for the possibility to be here today and this very nice conference that we are facing. And in particular, in this talk, I would like to consider the possibility to study the edge states that appears in spin-1 chains using scanning tunneling microscopes. So let's see if, yeah. So as it was mentioned from the very beginning of this conference, we have here two communities. On one side, the community of quantum magnets, and on the others, the surface nanomagnetism, and especially people from magnetic atoms. So I think it's quite worthy to ask, or pertinent to ask the question, can one actually build and prove simple spin models using these magnetic atoms? And I think it's worthy also to consider why studying these models. Charge and spin models are particularly important to study the interplay between magnetism and charge in condensed matter physics, since they allow to simplify these extremely complex problems, especially when the strong correlations appear. And among the different models, spin chains are very important, not only because they are one of the simplest models that can be analyzed, but they have a quite rich behavior and can show different states of matters as quantum spin liquids, hidden topological order, or the fractionalized edge states. And especially in regard to these fractionalized edge states, they can appear, for instance, in the integral spin chains, integral antiferromagnetic spin chains. And this will be the central topic of this talk, and in particular, they are one of the simplest consequences or effects of the many-body interactions in a system. So, as I said, these fractionalized edge states appears in particular in the spin-1 Heisenberg chain. And in order to see the nature of these states, one can go into the AKLT model introduced by Ian Affleck and co-workers in the '87. So even though it looks like a more complicated Hamiltonian, it has a great advantage, that is, it can be solved analytically. And what they describe using a very smart description is that this spin-1 chain with this extra term can be described as spin-1 objects that are built as two spin-1 half. So in the description of this system, it turns out that we'll have a pairing term of the singlets that joins every spin-1 half object, and then we have also the projection into the triplet state. But the important thing that appears here is that at both edges of the chain, we'll have one of these spin-1 half object that doesn't have any pair. So this gives place to the spin-1 half edge states. And in this particular model, in addition to these spin-1 half objects that are very interesting because they are high correlated states, and they have a fourfold degeneracy in the case of an open chain, since these two spin-1 half objects doesn't speak to each other. And on the other hand, if we are talking about periodic boundary conditions or a ring, they will interact between each other, and this gives place to a gap phase where the gap is precisely the Haldane gap. On the other hand, as we have seen this during these days in the conference, especially the first talks about the capabilities of STM, we know that nowadays it is possible to use this STM not only to probe or to look at the topography of a surface, but also to extract information about the spin texture, for instance, using the spin contrast imaging, also to manipulate these atoms on the surface to extract the transitions and then to make the spectroscopy of the system and even time resolve the dynamics of the system. So the idea is to combine these two possibilities. So I can rephrase the original question for a more particular case, that it will be, can one build and probe spin 1 antiferromagnetic chains? So and observe the edge states that appears in these chains. So there are several requirements that we have to satisfy. One of them will be, or the first one, is the possibility to build such a chains using a STM. But as we saw from the talks of Cyrus the first day, Marcus, and most of the experimental colleagues working on STM, such a spin chains can be built using different magnetic atoms. For instance, here we have manganese spin chains that are antiferromagnetic, iron spin chains, or even the ferromagnetic spin chains. So this is clearly within the experimental capabilities nowadays. So the second step, obviously, if we want to study a quantum model like the Heisenberg model, we have to build a system that is quite isolated from the rest of the world, so it keeps the properties of the isolated system. And at the same time, in order to probe the system through a tunnel current, it must be close to a metal, so we can pass a current through the system. But this introduces a problem, because the coupling between the magnetic atoms and the spins of the conduction electrons, this Kondo-exchange coupling, produces the screening of the local magnetic moment, and thus the so-called Kondo effect. This Kondo effect that appears as an increased resistance as we lower the temperature in the system has been observed also, as we have seen these days, using STM. And the main problem is then that the Kondo temperature, the characteristic energy scale of the problem, is usually quite large, and it can hide other energy scale related to magnetism. So to this difficulty, there are also additional consequences, and the main consequence, I will say, related to possible applications, is that this screening makes the magnetic atoms or the magnetic moment useless from a practical point of view, since it will disappear. One cannot use anymore this magnetic moment as a magnetic bit. So people have arrived to different solutions to reduce this problem. One of the solutions is to use thin insulating layer, typically a monolayer of an insulating material. Another possibility that has been already experimentally done is to absorb the magnetic atoms on a semiconductor, and a third possibility is in the form of superconducting substrate, where the superconducting gap prevents the low energy excitations. So even though we cannot fully isolate the system, we can build systems that are quasi-isolated and still resembles or keep most of the properties of the isolated system. So the final question, and probably the most complex, is to find the proper experimental system that it will have a spin 1, an isotropic spin 1. And let me, as we have seen these days, several transition atoms, especially transition metal atoms, that has been studied with STM techniques on copper nitride. That's one of the most common substrates these days. But we don't have the full table of transition metal atoms. So if we rely on DFT results, this corresponds to a recent paper of Joaquin Fernandez-Rosier and co-workers, where they studied the transition metal atoms on the copper nitride surface. And if we rely on these DFT results, we see that the magnetic moment is reduced with respect to the free atom. And if we are looking for a spin 1 system, that is a magnetic moment of 2, the two candidates will be the cobalt and the vanadium atoms. The problem is that, well, the data experiments on cobalt, and this experiment on cobalt shows that the Kondo peak at 0 bias with the inelastic steps and how they change with the magnetic field behave much more as a spin 3½ system than as a spin 1. So clearly from this, I will say that we can forget about the cobalt. So the other possible candidate will be the vanadium. And the other thing that is, or it can be derived from the DFT results, is that the magnetic moment is no longer localized on the d orbitals of these transition metal atoms. Part of the magnetic moment is localized on the neighboring atoms, even though it's not the majority. But still, the question remains if vanadium will be a good candidate for a spin 1. There are other systems that has been studied and presents spin 1. One of them is the cobalt-hydrogen complex on boron nitride. This system behaves as a spin 1, but it has additional problems. That is, especially it has a quite large magnetic anisotropy. Even one can observe the quantum spin tunneling induced by a transverse anisotropy term. And on the other hand, it still has to be tested experimentally if spin chains can be built on this substrate. The other possible candidates of the iron atoms on indium and timonite and the iron tallocyanine on oxidized copper surface may have similar problems, that is a quite large magnetic anisotropy, and still the possibility of building spin chains using these atoms. So, as I said before, the question still remains as what will be the perfect experimental candidate for having a spin 1. But let's for the moment, as especially being theoretician, let's for the moment forget about the complexity of the experimental problem, and let's consider that such a system can be built. So what properties can we expect? Here we have the Heisenberg model for such a spin 1 system, where I add this additional term that corresponds to the interaction between the first and the last atom of the chain. So one can go between the open chain boundary condition to the ring boundary or periodic boundary conditions, just by changing the parameter kappa. So In both cases, the low energy spectra of these chains depends strongly on the parity of the number of spins. So if we have an even number of spins, we'll have a ground state that is a spin singlet, and the excited state is a spin triplet. While this situation is reversed in the case of an odd spin chain. And in both cases, what one can find is that the singlet-triplet energy gap decays as the number of spins increases. And this happens in both in the ring and in the open chain. So in fact, if for a fixed number of spins, one study or close adiabatically the chain, one finds that the gap between the singlet and triplet increases. In addition, one can also check that this energy gap decays exponentially with the number of spins in the case of an open chain with a typical length that is of the order of 4, and in the case of a ring, the energy gap tends to a constant plus a correction of the order of n squared, where n is the number of spins, and this constant is nothing else than the Haldane gap. And the most interesting thing about these chains, as we mentioned at the beginning, is that the triplet states presents these fractionalized edge states with a finite length in this case, but we have these spin 1/2 objects just at the border. So we also know from the spectroscopy of magnetic atoms that the differential conductance is proportional to matrix elements between the two states involved in the inelastic transition. In this case, if we are talking about a transition between the ground state of the system, let's say the singlet state and the triplet, we'll have these matrix elements. But it turns out that in the case of a finite spin chains, these matrix elements are spatially modulated, and they are maximum at the border of the chain. And the direct consequence is that the differential conductance, as it will be measured in an experiment, presents this modulation of the inelastic transition. That is, imagine that we look at the conductance, putting the tip on the first atom of the chain, and one finds this inelastic step. Then as we move toward the center of the chain, the height of this transition decreases, reflecting the edge character of the excitation. The other thing that one should account for is typically in magnetic atoms, there is also a magnetic anisotropy present in the system. So let's consider first the possible effects of the longitudinal magnetic anisotropy, that in the case of a single magnetic atom, the effect of this magnetic anisotropy, imagine that we start with the easy axis that will correspond to a negative d, is that it favors the spin 1 projection plus minus 1 projection over the spin 0. While the situation is just reversed in the case of a hard plane anisotropy. For positive d, the ground state of the single magnetic atom will be the spin 0. So if we study how the local magnetic moment at the border of the chain changes with the magnetic anisotropy, one finds that it deviates from the hypothetical 1/2 value as one increases the value of the longitudinal magnetic anisotropy. So for positive d, it tends to 0, as it will be the case of a single magnetic atom, while for negative d, it will tend to 1. In addition, one also can have the transverse magnetic anisotropy that, as it has been discussed these days, it introduces this quantum spin tunneling that leads to a 0 expectation value of the magnetic anisotropy, since a bonding-antibonding combination is formed. But still, in the differential conductance, even in the presence of a small magnetic anisotropy with both longitudinal and transversal terms, one should be able to observe the localization of the inner excitation of the system. So the excitation, the amplitude of this excitation decays as one moves from the edge of the chain toward the center of the chain. And finally, another possibility will be to study the system with a spin-polarized current. And the spin-polarized current will have different effects on the system. On one side, it can produce a local exchange field that is proportional to the exchange coupling with the tip, so it will change exponentially with the tip distance, and proportional also to the polarization of the tip. Then, in addition, one also can have magnetoresistance, and this magnetoresistance will give place to an asymmetry in the differential conductance. And especially important for high currents, it can induce a spin transfer torque. So here I plot the differential conductance using a full polarized spin current for an even number and odd number of spins. And the first thing that we can observe is the asymmetry in the differential conductance in contrast to the case of an spin and polarized tip. But as we have here the differential conductance for the different positions of the tip, let's look to a particular example to see clearly the effect of the polarization, or an additional effect of the polarization. So the black curve corresponds to the differential conductance where the chain, when the chain is probed on the first atom, and the red one corresponds to the chains probed on the second atom of the chain. And the most fascinating result is the change in sign of the asymmetry between the neighboring atoms of the chain. And this is reflecting the staggering order that appears naturally in an antiferromagnet. So here we can observe how this asymmetry in the differential conductance changes with the applied bias voltage. So in both cases, we have a quite high magnetic asymmetry, and especially important in the case of odd spin chains where the ground state of the system is the triplet. But notice how, as we go between neighboring atoms, the first here in black, then the red one, blue, we are changing always the sign of this asymmetry. So just to conclude, let me say that the STM may prove the fractionalized edge states of atomically ensembled spin chains, and the spin-polarized STM can provide additional information and map the wave function of these edge states. And the big challenge will be to find the experimental system that behave as isotropic or quasi-isotropic spin one chains on this system. And finally, I would like to send the collaborators in this work particular Joaquin Fernandez Rosier and Christian Batista. And of course, thanks to you.